Hi, I'm Justin Rutledge, and I'm here to present the motivation, findings, and overall concept of my final project for the fall 2023 semester for the class Design and Analysis of Algorithms at the University of Tennessee Chattanooga. So the title of my paper is Analysis of the MD5 Cryptographic Hash Algorithm and Considerations of Alternatives. My motivation for deciding on this topic was primarily to understand the time complexity of the MD5 algorithm as well as other cryptographic hash algorithms, and compare that to the time complexity of the attack algorithms that were used to crack some of these or to break the hash algorithms. And what I mean when I say break is essentially find collisions, and in particular find collisions in a reliable, repeatable way. So MD5 is well known to have been broken for some time, and this paper goes through the analysis of the MD5 algorithm itself and the analysis of the algorithm used to break it. And the results that I've found are that both occur in linear time, big O of n, for both the MD5 algorithm and the attack algorithm, with one major footnote, that is the coefficient used for that linear time is dramatically higher in the attack algorithm based on the probability of finding a collision per iteration. And the paper goes into that. So what I essentially did was I went through a step-by-step of the pseudocode for the MD5 algorithm and determined the analytical time complexity, and then converted that to the asymptotic time complexity using the definition of asymptotic time complexity. And then after that, I took a look at the analysis of attacks on MD5 and its failure, in particular in August 2004 from a paper published that year and the next with the actual values used to find collisions, and then the methodology that team used, which is outlined here, and took the analytical time complexity of their step-by-step process, determined that it was somewhere approximating 8.8 times 10 to the 12th times n. And so this is the coefficient that I mean is just very high and leads to a fairly long time to actually run this operation, but it still is considered linear time complexity by the definition of asymptotic time complexity, which I found very interesting. After a discussion on MD5 and the MD5 attack algorithm, I go over the secure hash algorithm, or SHA, family of algorithms, which differs from the MD5 in that they are more secure, but they are functionally very similar. They take an input string and produce a fixed size output string in a predictable way that's one way that can't be reversed. The main difference is just a greater complexity in the SHA algorithms, and in some iterations, actually every one compared to MD5, there's a greater length of the output bit string, and this allows for a greater possible number of outputs too. So for, say, a 256-bit output string, there are 2 to the 256 possible combinations, which is just astronomically high, and the likelihood of a collision is very low, although SHA-1 has also been broken, and I go over the algorithm that was used to break that as well. Do a quick comparison. I don't go as in-depth with SHA as I do with MD5, but the final conclusion here is essentially that while the asymptotic time complexity is the same for all of the SHA algorithms and the attack algorithms, as well as MD5's algorithm and attack algorithm, the sheer size of the coefficient required to find some of these collisions means that it's really an intractable problem, despite having what we would think of as a low-class asymptotic time complexity. It was a very interesting conclusion. So time complexity, or asymptotic time complexity, doesn't always indicate the tractability of a problem. Anyways, that concludes the presentation. I was trying to keep it fairly short, so I hope you enjoy reading the paper. Thank you.